Okay, so the next module that we will talk about is the finite element method. Okay, so finite element method is, you have all heard the word, right? Finite element method. It's a standard method in many branches of engineering. Okay, so we'll talk about the history of this field, which comes under the overview, right? So the short form for finite element method everywhere you will find is FEM. Okay, and it's a relatively recent method in the sense that it's not very old. Partial differential equations, of course, hundreds of years old. The famous mathematician Courant is the person who began to work on it in the 40s, again for solving partial differential equations, and the engineering community began to take notice of it only by the 60s. Okay, so that's what I mean when I say it's relatively new. Okay, and finally, what is it? I mean, it is a method of solving Maxwell's equations with prescribed boundary conditions, which is what the earlier module was also about. Integral equations was also the same thing. So naturally, we want to find out what are the differences compared to what we have already learnt. Okay, so in integral equations, which we looked at, one of the very difficult things to deal with mathematically was Green's function, because it had singularities and all of those things, right? So the good news about Green's functions in FEM is that not there. You don't need to know Green's functions for FEM. In fact, FEM is formulated without Green's functions. Okay. In fact, it is not an integral equation. Okay. So the starting point itself is different. From Maxwell's equations, you don't convert all the way to an integral equation and then solve. You stop at the differential form itself and then solve, and we'll discuss details about it. So this is one big advantage, because Green's functions are actually very difficult to calculate in heterogeneous objects and so on. Then geometry, this is one of the major plus points of FEM. It allows you to deal with very complex shaped objects. So like this aircraft that has been shown over here. So these are actual simulations of, if you want to find out the radar cross section of an aircraft or something, this is how you would break up the domain. So here they have made these triangles all over the surface, and these are conformal to the object. Okay, so it takes the shape of the object. So it allows you to use a standard CAD software to mesh whatever complex object you want and work with it. So it gives you a lot of real life functionality. Okay. Then something that we look into detail as we go along, the computational cost is very low compared to integral equation methods. So integral equation methods, say you got a n by n system of equations. What was the complexity of solving integral equation methods? Those of you who have done linear algebra, n by n system of equations, what is the complexity of solving them? N cube, right? So integral equation was order of n cube, right? In FEM, this turns out to be almost order n. So how is this great feat achieved? Linear, you get a linear system of equations, but you can solve it in order n time. So what might be the trick? There is a speciality of the A matrix, of the system matrix, and that is the next point. The system of equations that you get is actually sparse. Okay, so question is, when I want to calculate the radar cross section of this aircraft, will you get a point for each?
Yes, the value for each.
A value for each triangle? No. So radar cross section is something that is defined for an observer far away. It's an integral over every little triangle over here. So every little triangle is an unknown that you are solving for, and that forms the system of equations. Once you get it, finally this guy observes a number, one value. So this sparse system of equations is what allows you to get this order n, and this also tells you that if I wanted to simulate and solve for a real life very complicated aircraft or ship or something, integral equation methods, they're just impossible to work with because they take so much time, order n cube versus order n. So I must point out this order n cube is for your textbook LU decomposition or whatever. The state of the art for this is something more like 2.4 roughly, okay, research level thing. Yeah, so I mean order n cube is textbook stuff, but you can do better, but not as good as order n. Then the storage of the system of equations, in the case of integral equations, for storing a n by n system you need how much memory? N squared, right. So, storage in integral equations was order n squared, whereas in FEM, because I have a sparse matrix, n equations, each equation sparse means very few entries are non-zero. So, the number of entries are FEM is again order n. So, both in terms of storage and computation, FEM is a big winner. So, I mean looking at this, naturally you should ask a question, if everything is so great about FEM, why did we bother studying this integral equation method at all? So, the answer is that the accuracy that you get with integral equation methods is much better. So, to get the same level of accuracy, you would need to discretize finer in a FEM than integral equation method. Okay. And we'll see that, we'll see a very good conceptual reason for that as we go along, that why is it that way. So, that's the price that you get for a sparse system of equations. Okay. There is no free lunch, and that's where you lose out. So, a lot of your commercial software, for example, the most popular commercial software is, for example, ANSYS or HFS as it is called. It is based on the finite element method. Now, they have some more modules which allow you to do integral equations here and there, but the way you are able to really work with very large electrical objects is FEM, because memory and speed are reasonable.